This lecture covers section 8.1 on sequences. This is the big push for the last unit of material, our sequences and series. We did L'Hopital's rule and improper integrals just to have those tools available to us once we get into the series test. So here, let's define what a sequence is. So definition. A sequence is a list of numbers that shows some pattern. Okay. The list is a function, say A of n, whose domain is the counting numbers n equals 1, 2, 3, and so on. The terms of a sequence are denoted A1, A2, A3, and so on. And A of n is commonly denoted curly bracket A sub n. Okay, so when you see this notation, you know we're talking about some sequence. Okay, so let's try an example. So we want to find the first 4 terms of the sequence. So A, say we have this sequence A sub n is 3 to the n over n factorial. Okay. So again, we're treating this as a function with domain values 1, 2, 3, 4, 5, 6, and so on, right? So to find the first 4 terms, we simply need to just substitute in 1, 2, 3, and 4 for n here. Okay? So what would A1 be? A1 would be 3 to the first power over 1 factorial. Now, what does this factorial mean? So you may have seen this before, but just a side note, factorial let's say 5 factorial. What this means is 5 times 4 times 3 times 2 times 1. Okay? 100 factorial would be 100 times 99 times 98, all the way down to 1. Okay? So you can see factorials are pretty large numbers, especially as the value of n gets larger and larger. Note that 1 factorial is just 1, and 0 factorial, which we may run into at some point, is equal to 1 as well. It's defined to be 1. Okay? So let's calculate this. What's 3 to the first? 3. 1 factorial is 1. Therefore, the first term in this sequence is 3. A2 would be 3 squared over 2 factorial, or 9 over 2 times 1 is 2. The third term, 3 to the third over 3 factorial. 3 to the third power is 27 over 3 factorial is 3 times 2 times 1, that's 6. So this will reduce. If we divide out a 3 from each of them, it's also 9 halves. And lastly, a 4, that's 3 to the 4th over 4 factorial, which is 3 to the 4th over 4 times 3 times 2 times 1. So we can do a little cancellation before we actually multiply. That 3 is going to cancel one of those. So we get 27 over 4 times 2 times 1 is 8. So the first 4 terms of this sequence are 3, 9 halves, 9 halves, and 27 eighths. Alright. B, let's find the first 4 for this one. An equals 4 plus negative 1 to the n. Okay. So what would A1 be? A1, just substitute in 1 for your n here. So that would be 4 plus negative 1 to the first, or 3. A2 is 4 plus negative 1 squared. Well, negative 1 squared is positive 1, so that's 5. A3 would be 4 plus negative 1 to the third power. Well, that just creates a negative 1 again, so that would also be 3. And A4, you can probably guess, that's also going to be 5. So there are the first 4 terms of that sequence. Okay, so finding the terms of a sequence is pretty simple. The reverse process would be, what if I gave you the terms and I want to find this little formula that calculates these terms? Okay, so this is known as finding the nth term. This just means find the formula for the sequence. Okay? So find the nth term of the sequence. Let's do A. 2, 5, 8, 11, 14. Okay. Right, so what we're trying to do is develop a formula, a little formula that will calculate these values that's dependent upon n, right? So, easy way to think about that is to identify which term of the sequence we're dealing with. So this would be our first term. So n would be equal to 1 in the case of 2. It would be equal to 2 for 5, 3 for 8, 4 for 11, and 5 for 14. So we want to create a little formula such that if we were to plug in 1, we would get 2. If we plug in 2, we get 5. If we plug in 3, we get 8, and so on. So let's think about it. We're going to try to just guess operations that we can do here on 1 that are going to produce a 2. So the most easiest that we can probably see is that if we multiply 1 by 2. So 1 times 2 gives us 2. But if we do the same thing for 2, 2 times 2 would give us 4. So that's not going to be, so 2 times n is not the explicit formula that we're looking for here. So let's think about what we can do to get these. So notice if we take 2 to the first power, that gives us 2. 2 to the second power would give us 4, so that wouldn't work. So let's think about it. What can we do here? Well, if we notice, we can multiply this by 3 and subtract 1 to get 2. So 3 times 1 is 3. Take away 1 would give us 2. 3 times 2 is 6. Take away 1 gives us 5. 3 times 3 is 9, take away 1 gives us 8. 3 times 4 is 12, take away 1 gives us 11. And 3 times 5 is 15, take away 1 gives us 14. So if we have this infinite series, our nth term would be 3n minus 1. Okay? So you just have to play around with these to get the appropriate formula, okay? Try to be clever with it. All right, so let's look at this one. 2, negative 5, 10, negative 17, 26. Okay. So let's do the same kind of thing. Here we can see we have some sign alternation. So 1, 2, 3, 4, and 5. Alright, so let's see what we can do. So again, we're not going to times by 2 here. Note that we do have some sign alternation in this, so we may have to have a negative 1 to some power, like we saw in the previous example. It just flips back and forth between positive and negative. So let's see what we can do. If we multiply by 3 and subtract 1, that'll give us 2. Multiply by 3, subtract 1 gives us 5. Multiply by 3, can't subtract 1 to get 10. So let's think about what we can do here. So let's think. If we, what can we do to produce these values? 2, 5, 10, 14, 26. Well, notice these values are almost perfect squares, right? So actually, if we do n squared plus 1, that gives us 1 plus 1 is 2. N squared, 2 squared plus 1 is positive 5, so we can just multiply by negative 1. 3 squared is 9 plus 1 gives us 10. 4 squared plus 1 gives us 17, and 5 squared plus 1 gives us 26. So we know to produce the values, we can do n squared plus 1. But we need to multiply that by some alternating power, right? So we can actually multiply the front here by negative 1 to the n plus first power. Okay? Why n plus 1? Well, we want the first one to be positive, right? So if n goes n, we need to have an even number here. So there is our sequence. Let's try this one. How about 1, 1, 2, 6, 24, 120. Will be our nth term here. Alright, so if you notice, numbers start out pretty small and then they grow pretty quickly. So we know a couple of functions that help us to make the value grow pretty quickly. So we can consider an exponential function, possibly. Or we saw with the previous example that factorials also grow pretty quick. So if you see this quick growth, we should be thinking exponentials or factorials. So we know that 1 to the first power is 1, but 2 to the first power is not 1. How about, so that might be out. We know that these terms here also really don't have too much of a pattern in regards to multiplication. So let's try a factorial. So what's 1 factorial? That would be 1. 2 factorial is 2. 3 factorial is 6. 4 factorial is 4 times 3 times 2 times 1. That's 24. 5 factorial is 120, actually. So you can check that. 5 times 24 is 120. 4 times 6 is 24. 3 times 2 is 6. So it looks like there's a factorial pattern that we get here. But it's kind of off by 1. So what we can do is subtract 1 from n first, and then use a factorial. So if we notice here, 6 take away 1 will give us 5, and 5 factorial is 120. 4 take away 1, 5 take away 1 is 4, and 4 factorial is 24, and so on and so forth. What about this first one? What's 1 minus 1? That's 0 factorial, and we found 0 factorial to be equal to 1. So this is our value there. And then last, let's do 5 halves. 5 halves, 15 over 8. 5 over 4, and 25 over 32. So what's this? Alright, so let's take a look. So we have the same values here, but we notice kind of it's increasing, then kind of decreases again. So notice at the bottom, if we kind of disregard these two terms here, how can we produce the top with our ends here? Well, this is just 5 times 1, that's 5 times 3, that's 5 times 5, right? So it looks like we're going to generate the top values by doing a multiple. But what about these guys? Well, notice that sometimes these fractions are given in a reduced form. So this is actually 10 over 4, right? And this would be 20 over 16, right? So you can see if we kind of desimplify this, right, reverse simplify, we get some pattern that looks pretty good. So at the top, it would be 5 times 1, 5 times 2, 5 times 3, 5 times 4, and 5 times 5. So at the top, we have 5 over. Now how do we produce these denominators? That's 2, 4, 8, 16, 32. Looks like it's multiplying by 2 each time. So that would be 2 to the first, 2 squared, 2 to the third, 2 to the fourth, 2 to the fifth. This would be 2 to the fifth. Alright, so you can see that this process is a little tougher than just plugging in values, of course. But if you play around with it enough, you should be able to generate those patterns. Alright, now let's talk about when sequences converge and diverge. All right, as we saw with the improper integral video, certain things converge and certain things diverge, and it depends on whether we get a finite value or an infinite value. So let's look at a definition. A sequence is said to converge if its terms approach a finite value. That is, if the limit as n goes to infinity of the terms in the sequence equals L, and L is finite, the sequence converges. Okay. So if you see a general trend in the values of these terms, then it converges. Diverges otherwise. The sequence diverges if L is infinite, or does not approach a specific value. So if the sequence, if you notice that this value is going to infinity or negative infinity, then we say the sequence diverges. It is also true that if this limit does not exist, that means if L does not approach a specific number, like it alternates back and forth between 2 values or 3 values, then it's also a divergent sequence. Okay? So determine if the sequence converges or diverges. So here the limit, the sequence is 1 over n. Alright, so to determine whether this guy converges or diverges, we need to check that limit. We need to check to see if that limit approaches some value or goes to infinity or just bounces back and forth between some values. So let's check the limit. Limit as n goes to infinity of 1 over n. Well, what is that equal to? Well, n is growing without bound in the denominator. 1 divided by a giant number goes to 0. So 0 is a finite value, therefore the sequence converges to 0. P, our series is 3n squared minus 2n plus 1 over n squared minus 1,000. Okay. So what is this limit? So recall that when we're looking for the limit as n goes to infinity of this guy here, all we would need to do is just check the powers in the denominator, right? The lead powers. If the lead powers are the same, recall that we take the ratio of the lead coefficients as our limit. Here's a 1 right there. So 3 over 1 is 3. Therefore, sequence converges to 3. All right, last one. How about negative 1 to the n over n squared? All right, so let's check this limit. Limit as n goes to infinity, negative 1 to n over n squared equals what? Well, this one's a little tougher, right? Because we have that alternation in the terms here. So infinity goes in. The top can be either negative 1 or 1. So this implies that negative 1 to the n over n squared is between negative 1 over n squared and positive 1 over n squared, right? So if we take a look at each end of this, right, the lowest it can go is negative 1 over n squared and 1 over n squared. Highest it can go here. Okay? So as n goes to infinity, we know the limit as n goes to infinity of negative 1 over n squared. Limit for what we're looking for, and limit of 1 over n squared. Well, what's the limit as n goes to infinity of 1 over n squared? Well, if we throw an infinity, this gets bigger and bigger in the denominator, so this is 0. And what about here? If we throw an infinity here, what's negative 1 divided by a gigantic number? Well, that's a number that's really close to 0, so this also goes to 0. So our limit is in between 0 and 0, which means it forces it to be 0. Therefore, this limit is 0, and the sequence converges. This is called squeeze theorem. We can also take a look at the graphs of these 8.1-Desmos. So let's see what happens with that. Okay, so we can see here the sequence of numbers. So here we have a of x is 1 over x. So it's going to plot some points, n and a sub n. So here, if n is 10 terms, we can see the first term would be roughly, actually 0.5, and so on and so forth. So you can see here the terms of the sequence evolving as we go, 1, 2, so on and so forth. So you can see here, if we increase the number of terms, what happens with these guys. So it's looking like they are kind of leveling off. And if we go up to 100 terms here, you can see that they never cross the axis. But in fact, they're getting closer and closer to the axis each time. So if we scroll in here, this guy was, the 92nd term was 0.01087. Here, the 93rd term was 0.01075, and so on and so forth. So you can see that they're decreasing a little bit each time. In fact, they're decreasing towards 0. So that's the deal with our limit, right? We took the limit of that sequence, and we found that it approached 0. Therefore, we say this sequence converges. Let's look at our other sequence. How about -1? How about the second one there? -1. To the x over x squared. Okay. So here, let's go back home here. You can see as we build the terms here, as we go, you can see we have the first term is some negative value. When n is 2, we get 0.25. When n is 3, we get negative 0.11, and so forth. So you can see here that the convergence happens rather quickly, right? So even though we have some alternation above and below the axis, it's still approaching 0 here. So for our last example, we got a limit that was equal to 0 from the squeeze theorem, and you can see that here. So as we go, 0.012 negative, then positive 0.01, so you can see it's decreasing a little each time towards 0. So that's the whole push behind convergence of these sequences. Okay, now let's look at some properties of these sequences. Some nice algebraic properties evolve from two convergent sequences. So suppose the sequences, say our first one is A sub n and the second one is B sub n. Converge. Then let's say and C is a real number. Then the following sequences also converge. First one, the sum or difference of the two sequences converges to the limit as n goes to infinity of a sub n plus or minus b sub n, which is because a sub n goes to some real number, let's say it goes to L, plus or minus b sub n goes to, let's say, k. L and k are both finite, therefore their sum or difference is also finite. The product also converges. Product sequence converges to L times K. The quotient will converge 2L over K, if K is non-zero, of course. And any constant multiple times either of them. Some constant times B sub n or constant times A sub n converges to C times K or C times L respectively. Okay. So let's do an example. Given sigma an is n plus 1 over n squared. Bn is 1 plus 1 over n to the n. And let's say C sub n is n times the sine of 5 over n. Okay. We want to find limits. So first one, let's say the limit as n goes to infinity of an plus bn. And the limit as n goes to infinity of bn times cn. So here we need to determine whether or not these guys are converging. So let's find their limits. So here, the limit as n goes to infinity of n plus 1 over n squared. What's that? Well, if we notice, if we plug in infinity, we get infinity over infinity. So we can use L'Hopital's rule to decompose this a little bit. This is using L'Hopital's rule. We'll take the derivative of the top with respect to n. That's 1 over 2n. And the limit as n goes to infinity for this guy, 1 over some giant number is 0. So the limit a sub n converges to 0. Okay. How about this one? Well, it's the limit as n goes to infinity of 1 plus 1 over n to the infinite power. To the nth power, excuse me. So this one's a little tricky. So let's look at Desmos and see what we get there. Right, we'll plug in our values here. So if we take a look at the terms in our series here, looks like they're leveling off. And in fact, this number is 2.604. Let's go out to 100 terms and see where it's going. So you can see here it's converging to this horizontal line. And the very last term is 2.705. Now, in fact, it can be proven that this number, if we continue it on and on and on, will go to E. Okay? So this limit is equal to E by Desmos. Last one, we're going infinity times sine of 0. That would be 0. This is infinity times 0. Also an indeterminate form. So we could apply L'Hopital's rule here, but let's just use Desmos. This limit n goes to infinity of this guy. Let's see what we get. right. So let's see what's happening here. What's happening with this limit here? So you can see some alternation. And what's happening as we alternate here? Well, you can see the values of this sequence are oscillating and growing in magnitude, right? The very last one is 100. It gets down to close to negative 100. We can assume this trend is going to continue forever and ever. So here, this series, this sequence will diverge. This is plus or minus infinity. In fact, it does not exist because of the alternation, right? It does not exist. So we say this diverges. Okay. So if we notice here, the limit an plus bn is simply the sum of the limits here. So 0 plus e is e. Okay. Now here bn times cn, note that bn does not, or excuse me, cn does not converge, therefore this diverges. Okay? Because bn's limit is a value, this guy just oscillates and gets larger and larger, so this limit is also going to diverge. All right, let's talk about two properties of sequences, and then we will break from here. Okay, so let's talk about boundedness first. We say that a sequence is bounded I abbreviate that BDD, bounded, if there are real numbers little m and capital M such that the terms in the series are between little m and big M. Okay? We say that it is bounded if all the terms in the series are trapped between basically two horizontal lines. If all the terms can fit between two horizontal lines, as we saw, maybe something like this. We'll have value for big M up here. Let's say little m is right there. If all the terms in the series, a sequence, are contained within those two boundaries, then we call it a bounded sequence. A sequence is bounded below if all the values are larger, but a sub n has no upper bound. Okay? And a sequence is bounded above if all the terms are smaller than some number, but an has no lower bound. Okay? So let's look. Determine if the sequences are bounded above or bounded below. Okay. Sigma an is 1 over n. All right, so let's think. Remember that n ranges from 1 to infinity, right? So we saw that the limit as n goes to infinity is 0. Therefore, the lower bound, little m, is 0. So we know that all the terms are less than or equal to, or should be greater than or equal to 0. Now, how about the largest term? What value, is there an upper boundary on this area, or this sequence, such that the terms will never be above that value? Well, the very largest that this sequence, the term that's largest that this sequence can pump out is 1, right? That happens when n is 1. When n is 2, it's a half. When n is 3, it's a third. So it's just a decreasing sequence. It decreases towards 0 here. But the biggest number it can possibly be is 1. So an upper bound here would be 2. So as long as we can find 2 values such that all the terms are in between, we say that this sequence is bounded. How about sigma an is 2 to the n? So again, n ranges from 1 to infinity. So at 1, we would get 2. At 2, we would get 4. 3, it would be 8. 4, and 16. At 4, we would get 16, and so on and so forth. So you can see here that this grows and grows and grows forever and ever and ever. So there is no upper bound. Big M is not applicable. However, is there a lower bound? Is there some lowest value that we can't go past? Well, the lowest that the sequence can pump out is 2, right? When n is 1, the lowest value we get is 2. Otherwise, it increases from there. So we know that a number that is a lower bound could be 1. So all the terms of the sequence are bigger than 1. So we have a lower bound, so we say that this is bounded below. Okay? Nothing to it. All right, so that's how you determine if a sequence is bounded. Just consider what's happening with the growth of the sequence, if there is any values that it can't go back past. The last property that we'll deal with is monotonicity. The definition: a sequence is monotonically increasing if an is less than or equal to an plus 1 for all n. Okay. So let's think about what this means. This means that the term in succession, so here, like if we had a1, this would be a2, right? 1 plus 1 would be 2. This would be a5, this would be a6. So all the terms in succession, the previous term is smaller than or equal to the next term. That means that a1 needs to be smaller than or equal to a2, which needs to be smaller than or equal to a3, and so forth. Okay? We say it's monotonic decreasing if a sub n is greater than or equal to an plus 1, okay, for all n. Or a1 is the largest of the values of the sequence, a2 would be next, and so on. Okay? So let's do some examples. Determine, there's a couple of ways to do this, right? So we want to show this for all n, right? So it's not good enough just to look at the first three terms. We have to do it for all n's. So there's a couple of ways to do this. We can do this using an algebraic approach, testing to see if this is true, or we can use the derivative. Remember, when the derivative is purely negative, we know that the function is decreasing, and when the derivative is purely positive for all n, the function will be increasing. There's a couple of ways to do this. So let's look. Determine if the sequences are monotonic or not. Okay? So we want to definitively say that for all the n's, for all the terms, one of these two relationships are true, or neither is true, right? So let's look at our first sequence. An equals n plus 1 over n. Okay? All right, so let's try to show one of the two of these. So let's think about what's happening here. If we were to list out some of the terms, right? So when n is 1, we get 2 over 1, which is 2. When n is 2, we get 3 over 2. When n is 3, we get 4 over 3. When n is 4, we get 5 over 4. So it looks like we have some decrease here, right? We have some decrease here. 3 halves is 4/3 less than 3 halves. Well, this would be 1.5. This is 1.33. This would be 1.25. So it looks like it's a decreasing function, right? But again, it's not good enough just to show a few of the terms. We need to show this for all values of n. So we're going to try to see if this is a monotonically decreasing function. We would want to test this relationship here. So that means that the nth term must be greater than or equal to the n plus first term for all n values, right? So let's test that. Well, what's an? An is just n plus 1 over n. So we want to show that n plus 1 over n is greater than or equal to, well, the n plus first term is just if we were to replace n with n plus 1. So it would be n plus 1 over n plus 1. We want to definitively say that this relationship is true, okay? So we can do that algebraically here. So we can cross multiply. This is our first method. N plus 1 times n plus 1 is greater than or equal to, this would be n times n plus 2. Okay? So at this moment, I'm not really satisfied that this is greater than or equal to that. I have an inclination that it might be, but who knows? So let's FOIL this out and see if we can't get some definitive proof for that. So if I FOIL out n plus 1 times n plus 1, I'll get n squared plus 2n plus 1 is greater than or equal to n squared plus 2n. Now, is this true? Well, let's look. N squared plus 2n plus 1 more, is that greater than or equal to n squared plus 2n? Yes, this is true, right? Because this is always going to be 1 more than that, right? Therefore, this implies sigma an, or excuse me, curly brackets an, is monotonically decreasing. Okay? So that's one way to do it, right? This is one way to do it, just showing this relationship. Another way is to show that the derivative of this function with respect to n will always be negative, right? If the derivative is always negative, then on our domain from 1 to infinity, then we should be able to conclude that. So if a of n is n plus 1 over n, what's the derivative of this function? Well, let's use the quotient rule. So it's the derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared. Okay. So let's see what we get. This will be n, take away 1. So that's negative 1 over n squared. You can see here that a prime is always less than 0, right? This negative 1 on top is always negative, and then the bottom is always positive. So this derivative is always less than 0, which implies an is monotonic decreasing. Okay? So again, the first derivative always being negative implies that this function decreases. Okay? That's a Calc 1 topic. Let's try one more of those. Same idea. Here we have an is n squared over n factorial. So here we see a derivative might be out of the question because that factorial, who knows how to take the derivative of a factorial. So here, let's try to determine whether it is monotonic increasing or decreasing using our the first method that we did last time. So we list the terms here. We can see n squared when n is 1, we get 1. When n is 2, we get 2. And when n is 3, we get 9 over 6. And so on and so forth. Right? So let's see what's happening here. We went up to 2. 9 over 6. What's that? Well, that's smaller than 2, right? So we had an increase to 2 and then a decrease back to 9/6. So we can see right away that this is neither monotonic increasing or decreasing. So here we can show that there's an increase and then a decrease in the first several terms. We can just conclude right away that it's not monotonic increasing or decreasing. All right, so that does it for this video lecture. Go ahead and start your suggested homeworks.